Okay, so let's go ahead and get started then. My name is Shirley Dyke. I'm the director of the MECHS, the Multi-Hazard Engineering Collaboratory and Hybrid Simulation. And today what we're trying to do is have a workshop focused on how to bring machine learning into this field. There's been a little bit of work in this area. It hasn't been extensive in the field of hybrid simulation specifically, but the idea is to try and make use of this as a way to expedite the work that we're doing to get more power out of the method. So first, I'll just make brief remarks for maybe 3 or 4 minutes, and then I'm gonna pass it over to our speakers. We have 4 speakers who volunteered to share their thoughts on this topic, share a little bit of their experiences with recent experiments that might give us some ideas to start our discussions. And then we're going to go into breakout sessions, and we're going to have a chance to discuss in smaller groups ideas, answer questions, and then we'll come back and try to summarize the discussions that we had briefly. And all of this we're going to do in about 2 hours. So the schedule is a little tight, but let's make it a lot of fun. Let's get as much as we can out of this time that we have together. So first, let me just briefly tell you about MECHS. MECHS has been around since 2017. We started with the objective of what I have written here, facilitating scientific advances, bringing the community together so that we can establish the theory of and the capacity for hybrid simulation. And it's really focused on multi-hazard engineering, but we've also see a lot of ways that we can use hybrid simulation for relevant other experiments. So we're trying to learn from those and bring that community in as well. The objectives of MECHS are written here. Some of the big things that we do are every time we have a meeting like this, and we've tried to have one every year, barring the pandemic. We made some different arrangements during the pandemic, of course, but we focus on having meetings, talking about things so that we can develop research agendas. We can describe what really needs to happen in hybrid simulation for us to make advances. We bring people together, peer-to-peer, institute-to-institute partnerships, and we share digital artifacts, models, papers, data, trying to encourage those things to be done. And we've had a number of activities. In 2017 in San Diego was our first workshop. We had about 50 people attending in that meeting. It was a 2-day meeting in San Diego, all the way up to 2020, where we had a pandemic, and then we went into some other activities. We had dissertation video competition, 3-minute video dissertation competition, and we had a workshop last year in wind engineering. In the summer, we had a workshop with colleagues in South America and Colombia, and now we're having our machine learning workshop. And we just try to hit different topics that people are interested in at different times. We have a website. I'm going to ask Manuel, who's been helping me organize this, leading the organization of it, to drop that link in the chat so that everyone has access to it. In Design Safe, you can get to it by going under NERI Community, and you see MECHS. Just click on that on the menu, and you'll find the information about MECHS. And there's a ton of information there. There's various pages. There's a publication library, which is probably one of the most valuable things for many of the researchers here. If you're new, there's a lot of learning activities, short videos, information about the terminology used in hybrid simulation, links to curricular materials, videos that can give you a strong background in different types of areas, like control, like signal processing and things like that. And so we've been building this slowly over the last 5 years, and we hope it's a useful resource for everyone here. The other thing that's there, though, is the research agenda. So we have a broad research agenda, which was last updated in 2019. And then we also have one that was focused more on fluid structure interaction. And that could be wind, that could be tsunami. And this is a committee report that is also posted. Both of those are easy to access from the main page. You don't have to dig through the website. You just look around on the main page and you'll find that. But really, this research agenda focuses on this question, what are the different topics or the different ways in which we need to advance this technology? And we broke it up into 4 areas: algorithms theory, enabling technologies, and community building. And each one of these topics we kind of hit each year. Now we're down in the bottom left, machine learning. That's what we're going to focus on today. So what I wanted to briefly say is, what are we here to do? Are we here to talk about how to advance machine learning? I don't think so. We're here to figure out how to use machine learning, right? We're researchers, we're engineers, we're probably not going to develop new machine learning algorithms. But what we can do is figure out how to empower, how can we exploit machine learning to empower the researcher and the engineer to optimize tedious tasks, time-consuming tasks, so that we can really focus on better engineering. How can we find models in the data or information in the data that might lead to a better understanding of the physics, right? And so briefly, I like to show this in some of my presentations, and I'm just going to repeat it here briefly. What we often do is the typical solution approach. We build a model, maybe it's a finite element model. We input our inputs. We input the forcing function or whatever it is into our model, and we get an output. And that's what we learn to do in our classes, right? And that's what we learn to do for many of our research projects. But machine learning turns that around, and we say there's an input that we know, and there's an output that we know, but what we don't know is that process, that model, right? This is the machine learning approach. We're trying to find the process. And so if we can find that process, then we can spend our time focusing on gathering good quality data and focusing on the engineering that we can learn from that problem, right? So that's just, in a simple way, that's the way I like to think about it. We're trying to find the process, right? We hope that by finding that process, we're going to be able to reveal or understand the structural behavior better, right? For the most part, we're structural engineers, wind engineers. We're doing those types of things. So we want to understand better how to build these structures. And we want to improve the hybrid simulations that we do so we can do that. And we want to learn more from the tests and our data. So we're not trying to do machine learning to do machine learning or to advance machine learning, but to figure out how to apply it to the problems that we want to solve, right? So what are we going to do today? First of all, we have a few speakers. Each is going to give about a 5-minute presentation. I don't think that we're going to spend a lot of time on Q&A though, because then what we'll try to do is go straight into our discussions. Let's see how the timing works out, but if there's time for questions, we'll certainly do that. But then we're going to break up into group discussions, and we're going to focus on, we can use these questions at the bottom here, which will be given to the groups. These are going to be the questions to maybe start the discussion. You don't have to stick with these questions. They're simply a way to get us started talking, okay? So one thing that I do want to mention is that in October next year in the US, there's going to be this NEARI Research Summit. And this is October 6th to 7th. And what I've written on the right here is the important thing, that what I'd like to try to do is have a session or a couple of sessions that are focused on hybrid simulation during that summit. And we do have funding to support travel for several US participants. But what this means is that we need you to kind of vote for the session. So first of all, those are the dates. Take note of that, do a screenshot of that. We'll email it out later as well. But you're going to get a survey link, which I think Manuel can also share that. And with that survey link, you can choose many sessions, but if you choose highly on the MECHS session, then we might get selected, okay? And then we'll have some opportunities and some funding for people to go to that meeting and to go to the session to participate with the MECHS group. So I'd appreciate if you could take a look at that and fill out the survey so that we can do something like that. That would be really interesting. That's where it is. Those are the links, but we're definitely putting them in the chat already. So if you're interested in joining the announced list and you did not get this through the MECHS announced list already, then just send us an email at mechs@purdue.edu and we will add that to the list. Okay. So at this point, I would like to see if there's any urgent questions, and if not, what we'll do is we'll jump straight into the speakers. I have to get out of this. Okay, there we go. I'm going to stop sharing and we're going to pass the ball over to Jim.
Yeah, hi Shirley, this is Jim. I sent you a chat. I was going to have Safwan present. I had kidney stone mishaps this morning there, so sorry about that. I'm here, but it's best if Safwan, he's done all the work, so he's well qualified to get the credit. But thank you.
Sounds good.
So can you see my screen? So this is Safwan.
Yes, we can. It's not in presentation mode, but maybe you want to put it in presentation mode.
Okay. Is it fine now? Okay, so thank you, Professor Ricles. So my name is Safwan, and I work with Professor Jim Ricles. So most of my research is about real-time hybrid simulation, and I will be showing you a way where at Lehigh we managed to integrate real-time hybrid simulation with machine learning. So including the soil structure interaction, especially if you have a building and you're trying to assess the behavior of the building under multi-natural hazards, you want to include the soil structure interaction, and you want to know the response of the building if you include the behavior or the interaction between the building and the foundation. So here is a real-time hybrid simulation case study. So you have a 40-story building, steel building. You have 4 basements, and you have 40 stories above grade. And the building is located in Los Angeles, and it's designed by SGH. And the purpose of this study is to improve the behavior of the building and assess the performance of the building under multi-natural hazards. So if you look at the building, we put nonlinear viscous dampers highlighted in red between each outrigger column and outrigger in the building. And we use real-time hybrid simulation to assess the behavior of the building in real time. So here is what it boils down. So you have the building and you have the soil underneath. And in your hybrid simulation, you want to include, or you want to see the behavior of the full system, as you can see in this slide. So why hybrid simulation? So you will be able to include or account for the full dynamic of the system, and you will be able to include only the critical part in your hybrid simulation. And it's especially good if you have a rate-dependent device. So in this study, you have a nonlinear viscous damper, and you want to be able to do the hybrid simulation in real time because the behavior of the device is rate-dependent. So the challenges, so if you want to include the soil structure interaction in the numerical substructure of the hybrid simulation, you will end up with many degrees of freedom, with many elements that trying to do the state determination of or solving the equation of motion, it will take too much computational effort that is prohibitive in the hybrid simulation. So, and if you want to include the soil structure interaction with the far field, and if you want to use the shake table, it's going to be difficult. So we want to go with the hybrid simulation approach. So here is how the analytical substructure looks like. So you have the experimental one is a full-scale nonlinear viscous damper. You have the outriggers. You have the other dampers in the building, model analytically using an explicit-based online model updating approach. The model has almost 8,000 degrees of freedom, 3,000 elements, and we use reduced order modeling. You have the geometric nonlinearities, the mass, and the inherent damping of the building. So here is the framework. So on the right, you have the experimental substructure. On the left, analytical substructure, you have the building, and you have the soil underneath the building modeled in a neural network. So here is how it looks like. So you have the building. Here is the full model. So we started 2D, but eventually we will migrate to the 3D model. So you have the building, 344 nodes. This is the structure. The soil underneath, you have 1,600 nodes. You're trying to replace the soil with a neural network, as you can see in the middle. So you keep the building, but the foundation underneath and the soil modeled in neural network. So you end up with 6 outputs for the interface between the building and the neural network. So at the beginning, the foundation on the soil, more than 1,600 degrees of freedom. But if you have the neural network, you'll end up with only 6 outputs. So this will enable you to solve the equation of motion faster and be able to run it in real time while accounting for the soil structure interaction. So here's how the training, I guess everyone is familiar with the training of the neural network. You'll end up with a large error, and with time, more training, the error goes down. So here is the soil characteristics underneath the building. You have the shear modulus, skin friction for the piles, and the unconfined compressive strength. So you have the results, you have the earthquake. So here is the bedrock acceleration, and here is the results. So this is the roof displacement. So you can see that if you include the foundation or if you do not include the foundation, there is a difference. And this is the motivation why you need to include the soil structure interaction in your hybrid simulation. So if you look at the peak story drift, again, you'll see a difference if you have the soil structure interaction versus not. So on the right, this is the response of the damper. Again, including the soil, the behavior of the damper is different. On the left, you have the pile force versus the pile head deformation. So this is at 2 different locations. So that was the earthquake. The other implementation is the wind. So for this building, we got the wind tunnel test, the force history, the wind force from Florida International University. So they have a wind tunnel. So we had a small model of the building. So here is the floor force at full scale, the time history. And here is the roof displacement when you have the foundation and when you do not have the foundation. Again, if you want to include the foundation, you'll end up with a different answer. So this is the motivation why you have to include it in hybrid simulation. Again, the behavior of the damper on the right with soil structure interaction versus not. And here, so if you put the nonlinear viscous dampers between the outrigger and the parameter columns, so the purpose is to reduce the accelerations. And if you have the soil structure interaction, you can see that the acceleration is slightly going up. So the benefit of adding the dampers is slightly diminished when you have the foundation. So here is the verification. So you have the neural network and you're doing hybrid simulation. You have to make sure that you're getting something correct. So acknowledgements, all of this research has been done at Lehigh, and the financial support comes from the NSF. So thank you.
Thank you very much, Safwan. I'd like to go to the next speaker, which the next speaker is Professor Jin-Song at the University of Oklahoma.
Thank you very much, Shirley, for the opportunity. Good afternoon, everyone. Could you hear me?
Yeah, we can hear. Can you put it in full screen mode?
Okay. Let me see. Let me know if the slide is moving. All right.
Good.
So,
Perfect.
okay, thank you. So could you see the second page? Acknowledgements to
Just
co-authors.
fine. Yes.
Okay, great, great. So everybody, first of all, I'd like to acknowledge my team. And we have a ResearchGate project page for you to check out publications. So today in this very brief introduction, I'd like to talk first about IML. So interpretable machine learning. There's no rigorous definition yet. However, our understanding of interpretable machine learning is the best of both physics-based models and traditional black box type of machine learning. Okay, over the years, we have been developing our work, and the interpretable machine learning area has been growing rapidly, and there's some redundancy in nomenclature. For example, leading researchers have identified informed machine learning or interpretable machine learning, and they educate us that they see their similarity. So I use this acronym here. It could be interpretable machine learning, and it also could mean informed physics, informed machine learning. So with this, I'd like to focus on the scope of work. We have been limited, focused on universal approximator, the sigmoidal neural network, because this is the most basic, this is the foundation for approximating nonlinear functions. So we focus on answering two key questions. The first is the number of hidden nodes, which is not given in this universal approximator theorem. And also, we are very interested to know the initial values of weights and biases for the training to start with. So I'd like to use this table 1, which I will mention down the road, okay, as a motivation. There are lots of domain knowledge in our applications of how we can utilize the domain knowledge to set up a neural network so that we have an idea about what's going on, why we define the neural network architecture in a way, okay, and so that a neural network will no longer be a black box. And also, we intend to provide practical guidelines so that you know, we can save a lot of time to be efficient. So with this said, first of all, I'm sorry. Okay, I'd like to review the capabilities of sigmoidal neural network. I'm giving you an example. If we choose two hidden nodes by defining their weights and biases like this, their sum, their linear sum, actually will lead to constant 1. So this is the simplest example to show that there are lots of insights that can be provided algebraically. So by doing this line of work, we have come up with the so-called neural network prototypes that can be used repetitively, that actually do not require training anymore, because we prepare them beforehand for use in practice. And so when we deal with polynomial fitting for basic arithmetic operations, et cetera, along this line, we know what to do. We know how to set up neural networks, how to assign initial values. Okay, and to complement algebraic capabilities, let's take a look at geometric capabilities of sigmoidal neural networks. So here, I'm not going to go through all three items A, B, C, but just taking item B as an example. How can we approximate a hardening type of nonlinearity? Here, we're utilizing two sigmoidal functions by shifting them through adjusting their biases value, and then taking the active range as such, and also removing the constant level that we just talked about by using two hidden nodes. Okay, so in total, using 4 hidden nodes, we should be able to capture a hardening type of nonlinearity. So we have other prototypes built, 3 of them built to individually or in combination to approximate, for example, 10 types of nonlinearities, including linearity that often are useful in system identification. So coming down to the last portion of this presentation, in summary, over the years, we have been interested in developing interpretability elements. We call them elements. So first of all, we have a collection of useful basis functions and features in system identification in approximating nonlinearities. Okay, so the examples were given previously in table 1 and also the figure I just showed. Okay, and then we come up with neural network prototypes that are derived beforehand, that are not trained. We derive them beforehand. Okay, so that we can use these prototypes as efficient as building blocks, modeling building blocks, such as springs, dampers. Okay, and we want to use them that way. So with these two done, how to make things happen? So in reality, when we have experimental data, for example, in a force state mapping setting, when we want to approximate restoring force, nonlinear restoring force as a function of displacement and velocity, this is just an example. We could introduce a user in the loop, to compare what we already prepared for the prototype's capability with the features observed in data. Then we can come up with strategies. We selected these 2 prototypes and we combine them together. Okay, concatenate them together to increase the width of the neural network. And from time to time, we will have to add, different layers. So this is how we do it. So this is the last slide of this presentation. Interpretability in this work shows up in 2 aspects. One is domain knowledge in engineering mechanics. The other one is domain knowledge in applied math, in terms of capability of sigmoidal neural networks, and also data-driven. A data-driven nature in our work shows up in the not only in the training itself, but also in the dominant features in the data we want to extract, so that we know better what prototypes to select. Okay, so over the years, we also have been seeking justifications in our work. Okay, and also continuous development currently is with my computer science collaborators in robotic kinematics. Okay, so currently we have been moving to 3 inputs for hidden layers. Okay. With this, thank you very much. for this opportunity. And I look forward to the discussion, to learning from you.
Thank you very much, Jin-Song. We're going to next go to Ali Imanpour from the University of Alberta. And by the way, there are people asking questions in the chat for the speakers. If you have a question, drop it in there. And if you would like to provide a reply as one of the speakers, go ahead and do that as well. And then we can all kind of see the answer. So if we have time at the end, we'll try to ask a few verbal questions. Thank you, Ali.
Okay, thank you very much for the opportunity. Can you hear me and see my screen?
Looks fine. Thank you.
Okay, thank you very much. My name is Ali Imanpour. I'm a professor of structural engineering at the University of Alberta. And I'm going to talk about a new machine learning based technique that we proposed, my student Fardad Mukhtari and myself, to improve the way that we've been doing a hybrid simulation, which I'm going to call conventional hybrid simulation. So basically to improve conventional hybrid simulation. Okay, here's the agenda of my presentation. I'm going to give you a brief introduction and the motivation behind this, this technique. Then the objective of the proposed technique, and then I will show you the architecture and the key components of this machine learning based hybrid simulation technique, and show after that some results to verify and also to demonstrate this proposed technique. And then I will conclude with main basically scientific contributions and some ongoing and future research areas. Okay, a hybrid simulation sits somewhere between quasi-static testing and shaking table testing when it comes in terms of testing cost, and also the realistic response that we're expecting under random excitation such as earthquake acceleration. So it's basically gives us a trade-off between kind of complicated shaking table, but at the same time more accurate results coming from shaking table testing, and probably less expensive quasi-static testing, but on testing that's done under predefined displacement that may not represent what we expect under seismic loading. So, but in conventional hybrid testing, we have some concerns. Number one is that the results can easily become biased because of the selection of the experimental component or experimental or physical substructure. The way that we typically do conventional hybrid testing is we identify one of the elements that are expected to yield become nonlinear or sometimes become unstable, and then we put that physically model that in lab, run the laboratory testing, and then the same time, I'm going to focus on pseudo-dynamic hybrid testing. At the same time, we run our ground motion and numerical substructure. So you see an example here, a brace frame, a concentrically braced frame example, where we had concern about the instability response of the columns, and we removed one of the columns. We tested in the lab that you see on the right-hand side of your screen. The test went well, of course, and then we saw the buckling of the column as expected. The right-hand side column, the one that we physically tested in the lab. But the left-hand side column could have also buckled if we were modeled that physically modeled it in the lab, if we had enough basically sufficient equipment in the lab to model two specimens. And it could be the displacement response could be a little bit different because of a different displacement coming from a different ground motion, and some other numerical assumptions that may have changed the result. So we could have had buckling of the left-hand side column. The other basically concern, which is basically a general concern about numerical simulations, and in particular in hybrid simulation, is associated with the elements that we numerically model in conventional hybrid simulation. And that's the dynamic characteristics of seismic fuses or elements that are going to yield under seismic loading. So inherently, seismic earthquake induces very complicated, random, basically response in a structural element, and it can basically creates different types of cyclic characteristics or trigger different types of cyclic characteristics. One of them is cyclic hardening, and in particular in steel that can depend on, like, highly depend on the type of loading that we are applying. On the right hand side of your screen, you see the response of physical testing, a buckling restream brace, one under a nice cyclic loading pattern at the top, and below another test, the same BRB, this time under a seismic induced deformation. If you look at the forces, maybe it's not on the screen, so maybe it's not so clear, but if we zoom in a bit, we're going to see that the force at a given strain is not the same between two loading protocols, and that's the reason behind that is the type of loading protocol that creates basically different cyclic hardening in BRB. So the question is, what type of loading protocol in general we should use to improve or to calibrate our numerical model, and in the context of hybrid simulation or seismic fuses that are not going to be physically modeled in the lab. So there have been to address some of these concerns, there have been different methods developed in the past, and multi-element hybrid simulation that you see on the right-hand side of your screen in the first row, and also geographically distributed hybrid simulation, so to basically, which is shown in the middle, to basically as alternatives for conventional hybrid simulation that you see in the first row on the left. But there are some basically limitations, communication time delays, and also equipment facility constraints, and so on. So this basically these proposed method and also concerns that I mentioned led us to propose a method that is based on a machine learning technique which leverages the experimental data that we produce real time in the lab during our conventional hybrid testing, in order to predict the response of the other seismic fuses that are not physically modeled in the lab and typically in conventional hybrid simulation are modeled in the numerical substructure. So that's what you see on the bottom left of your screen, where we create basically multiple substructures, and we use machine learning, numerical simulation, and physical testing in order to predict the seismic response of the structures. So I'm going to go a little bit more in detail of the proposed technique here with an example of a two-story buckling restream brace frame. You see on the left-hand side is kind of a typical way of the modeling of a BRB, which we call it reference model in the context of our work. Then we create three substructures. Number one is a numerical substructure, which is physics-based, using equation of motion models that solves the dynamic problem, and models at the same time mass damping and the stiffness of a almost elastic elements such as beams and columns in this particular example. Then we took out one of the BRBs, which is our seismic fuse that's expected to yield under seismic ground motion. We took off one of the BRBs, in this case, story 1 BRB, and then we test that in the lab. And the data produced from our the experimental specimen, which we call a physical twin in this example, is communicated to the numerical substructure, similar to our conventional hybrid simulation, at the same time to our data-driven model, which is shown in the upper right corner of your screen. And that data-driven model is basically reproducing the hysteresis response of other similar seismic fuses that are similar to the one that we are testing in the lab. So this guy here, which we call digital twin, passively trained using past experimental data. So we leverage our available experimental data, and during the hybrid simulation on the fly, we update its prediction capability using recursive model updating technique in order to better predict, for example, that cyclic hardening that I mentioned, while the ground motion is affecting our structure, and we are producing data, real-time data in our physical twin. So a little bit on the brain of that model. We use a Prandtl-Ishlinsky hysteresis model, which is a simple, elastic, perfectly plastic model. You see the equation that's basically governing the response of the hysteresis model. We combine multiple PI model together, and in order to produce the restoring force of the component that's going to be simulated into that data-driven or digital twin in our platform, in our technique. So what it does, basically converts this combination of these PI models or stub operators. It converts the hysteretic nonlinearity into a unique one-to-one mapping problem, which is favorable for machine learning algorithm, and we can basically leverage that during real time during our hybrid simulation. So that PI model is combined with a sparse identification algorithm in order to find which component or which set of components or stub operators are important or are dominating or are giving us a better response, a better hysteresis response. So this combination is done in that library MECHS that you see at the bottom left of your screen. So we put all the stub operators there, and we use a sparse regression algorithm in order to pick the stub operators that are gonna basically help us to better predict the response of our hysteresis model. So this eventually, what comes out from this equation is the output signal or prediction of restoring force. So once we implement this technique, as I said, we also use real-time recursive model updating in order to improve what we already predicted using PIs in the passive training technique. So I'm showing you a verification. We've done a few verifications. This is one example of those verifications. The upper, the first row on your screen, what you see is our reference model, which is a two-story buckling restraint brace frame. And the way that we modeled it a little bit to the right, we created the OpenSees model fiber base of almost elastic elements, beams, and columns, and then mass damping and in our model there. Integration is done there using our equation motion solved there. And then we created an Abacus model of BRBs which basically talk to our numerical substructures. That's our reference model. And then the bottom row, what we created is our new proposed hybrid simulation technique. We use a virtual hybrid simulation technique, and this for the same two-story BRBF. In the middle, what you see is the numerical substructure, very similar to the reference model. To the right, we have the BRB model, again in Abacus, which is our virtual specimen in this verification example, and we put our data-driven model in parallel to our OpenSees model and Abacus model, and connect all of them using UTSIM platform. And ground motion is run under in this numerical substructure. Displacement is sent to our BRB in Abacus. The force is basically predicted using numerically in this verification, and then it's communicated to our numerical substructure and at the same time to our data-driven model in order to predict the response of the second story BRB real time. So some results briefly. What you see here, that two-story buckling restraint brace frame at the upper, the second story response, including story drift and also hysteresis response, and the first story is displacement and hysteresis response. What I would like to highlight here is, well, first of all, is that if you compare a reference model, which is black, and the red model or proposed model, which is red, you see a good prediction by the proposed method. We remove that recursive model updating, which is an updating our prediction on the fly in one of the verification, and we created a model that is only passively updated, and that's given in blue to the right of the hysteresis model that you see. And as you can see, that recursive model updating can is significantly improving the response of the prediction capability of in the proposed technique. Okay, to conclude my presentation by using substructuring concept, we combine three basically a numerical substructure, a data-driven model that we develop, and also an experimental specimen, and we connect them together, and we basically propose the method to update in real time the response prediction of data-driven model in order to predict, for example, cyclic hardening parameters or properties that are dependent on the type of loading that you apply during hybrid simulation. So this technique can overcome some of the concerns that I mentioned, for example, the bias response due to the numerical modeling of the other critical elements in typical and conventional hybrid simulation, can improve the prediction of cyclic hardening in particular in steel structures, and it can offer a computationally efficient and economical compared to other proposed techniques, because this technique is basically an integration-free technique that is helping to significantly improves the computational time and computational effort that's critical during hybrid simulation. So I would like to acknowledge the financial and in-kind contributions supported by NSERC Canada, University of Alberta Steel Center, University of Toronto, UTCM team, and Polytechnique Montreal's the data provided by Polytechnique Montreal's researchers. Thank you very much.
Thank you, Ali. Let's move on to the next presentation, which is Mao Cheng. I knew your first name. I was looking for your second name. Sorry, Mao Cheng. Thank you.
Can you see my screen?
Looks fine.
Sure. Hi, everyone. My name is Mao Cheng, and I'm a student from UC Berkeley, and my advisor is Professor Tracy Becker. My topic today is the model updating using LSTM for initial selection. As we already know, the hybrid simulation divides the experiment into two parts, the physical test part and the numerical simulation part. The point of hybrid simulation is that the behavior of the experimental test is less well known, and sometimes there's some similar elements or material in the numerical simulation as well. And in this situation, we use the model updating that use the experiment part to generate some data and use this data to update the parameters into the numerical simulation. And this model updating hybrid simulation can improve the accuracy of the whole test. However, there is still something can go wrong. The model updating hybrid simulation is not the perfect solution to every problem. The first one is there could be inappropriate initial parameters in the model, and it will lead to some unstable analysis or even the failure of the numerical simulation. On the left figure over here, you can see the blue line is the failing result of some parameters, while it can go to very big or small numbers, while only the red part is a proper range of it. To solve this question, we can use a Walker-Cave, which I will introduce later. And the second problem is the limitation of the pre-selected numerical model. And if we select a model, we cannot capture the features that over the boundary of it. For example, when I get some experimental data on the right-hand side, I have the history loop like this, and I'm trying to use a linear spring to fit in this data. It's definitely not a very good idea because I cannot capture the damping or the energy dissipation in the hardest. And we have proposed to use LSTM for the initial selection to solve this problem. And you may ask, what is Walker-Cave? And Walker-Cave is actually the weighted adaptive constraint uncentered common filter. It combines the constraint, uncentered transformation, the weighting factor, and adaptive calculation. There are a lot of great work and research in the model updating. And for example, Professor Dake's research group has done a lot of fascinating research in the model updating using not only the original UKF and the constrained UKF. And we have done the same thing over here. We have added the constrained uncertain transformation into the circle over here. And then in the measurement transformation session, we have added weighting factor. And in the state correction, we have added a adaptive function for calculation R and Q, which are two matrices in the uncertain common filter. We are numerically simulating the coronal bridge model, which is the picture on the left, and we have physically attached the one bearing of it, which is on the right. This part is in collaboration with Camille Lopez-Royce. And the way we validate our model updating is trying to test the whole bridge with a physically test on the bearing on column 13, which has the largest displacement, and put other bearings into the numerical simulation. And we update the properties of these other bearings during the test with the experimental data. And then we collect the displacement time history from the numerical simulated bearing and retest the bearing with this time history into the physical test. For example, we can pick column number 5 bearing into the physical test again. And after that, we compare the experiment hysteresis with numerically updated hysteresis. And the figures below the effective of the original UKF on the left and the walk UKF on the right. We can see the result is very similar to each other. And then we should take a close look into the change of the parameters during the test. And we can see the red line is from the original UKF and the green one is from walk UKF. We can find that in the walk UKF, the convergence of all the parameters is much faster than the original UKF, and it is actually a good signal because the faster the convergence of the parameters, the stabler the model is. And then we have come to our new session, because in the full setup, we are not only going to test the shear force like in the first phase, we also need to consider the rotation and axial load. And it leads to a new challenge because all the degree of freedom, including the axial, shear, and rotation behavior, is coupled with each other. And we have found limited research onto that. So what model should we use? And how do we find the most appropriate model? To solve this problem, we try to use the LSTM or the recurrent neural network to do that. The recurrent neural network is a repetition of the neural network for each time step, and we feed the displacement time history as well as some bearing parameters as input, and it will generate the force feedback as an output. The LSTM is a variant of the original RNN, and in our research, we train this model just by the experimental data instead of we generate some data set from the OpenSea simulation, because in this way we can reduce the subjective bias greatly. And here is our result from the fitting. We can see on the left, we can see, and on the right, we compared the real experimental data with GRU, LSTM, and the Bookworm model from whose parameters is from genetic algorithm. We can find the LSTM model has a better capacity of capturing some nonlinear features. For example, the hardening at the two ends of the left recut and the damping on the right picture. However, because the LSTM is a very complex and large neural network, it's less explainable, and it requires a lot of data to train to reach a good result. So we believe it may not be that suitable in our case, particularly for the directly use of the LSTM model into the hybrid simulation. But we can generate some data points and find the expectation of the behavior of our element during the test, and we can use that to have a better model selection. And that's my presentation. Thank you very much.
Excellent. Thank you to all the speakers. I think this gives us a lot of good meat to talk about during our breakouts. I know that Manuel is going to go ahead and post the questions that I had shown earlier in the chat, just so that everybody has them handy. And in a minute or two, Herta is going to automatically put everyone into breakout sessions. We're just going to break the group up into 3 sort of randomly assigned breakout sessions. Each has a leader. So Gabby, Scott, and Gaston are group leaders. Each of them has a student who's also going to be helping take notes. And take about 30 minutes and just brainstorm, discuss the things that are interesting, things that you have questions about, share ideas, and then we will come back here and just give a 5-minute summary. So you can talk 30, 35 minutes. At about